again. Okay. So today we are going to discuss few questions about one second. So I think this is the question which states that a heavy uniform bar of mass m rests on the top of the identical rollers. So we have two rollers on the left and right, and let us call this as roller on the left and roller on the right. And there is a uniform bar of mass m which is placed on it, and the total length of the bar between the centers of this roller is given as 2L. So if C is the center of this bar, then mg will be acting downward direction, and we can divide with respect to this mg, that on the left side there will be length L and the right side there will be length L, and there will be two normals n1 and n2 with respect to both r1 and this r left and r right. And as a coordinate system, we can assume that the center of mass is, let us suppose, our x is equal to 0. So on the right side we are going to get x is equal to plus L, and the left side we are going to get x is equal to minus L. And we assume that the center of mass is displaced by a small amount x of t towards the right side. So we said let x of t be the displacement of the center of mass from the midpoint towards the right. Okay, the session was interrupted, so I hope now it doesn't happen, hopefully. So initially we can say that it is said in the question that initially the bar is held at a rest such that its center is at a distance of x naught from the midpoint of the rollers. Okay. So at time t is equal to 0, so we are given initially at t is equal to 0, we can say that our x naught, x at time t is equal to 0, that is x of 0, is given as our x naught, and its first derivative will be giving us 0. So it means at that particular moment its velocity is 0. So let us rename this as left and as right, much more easier. So let us write the equation for the normal forces. So we can say our normal forces, like we said, on the left side we are having n of L, and the right side we are going to have n of R. Therefore, and the total weight mg is acting vertical downward. Therefore, we can write equation as our n of L plus n of R is equal to our mg. This is the equation of our this, and there is the entire motion is on the x-axis. So on the y-axis there is no motion, or we can say vertical motion. Therefore, we can say that for equilibrium, it is mentioned, or we can draw a conclusion from the question, that there is no vertical motion. Therefore, for the equilibrium, if we take the moment about the left roller and toward the right one, okay, so we can say taking moment about left roller and left roller, which means at x is equal to minus of L. And for that we said that there is a moment of x, therefore we can say that distance from left roller to center of mass is, because there is a moment of x, so therefore we can say x minus of L, which gives us x plus L. So from the left side we said there is a slight movement towards the right side, so this total distance will be now x plus L. Therefore and we also know that the distance between left to right roller, this total distance is about 2L, which is fixed, it is not going to change. Therefore for equilibrium we can write the moment equation, that is normal to the our right roller will be our 2 of L is equal to our mg and x plus L. And from here we can just write it as n of r will be equal to our mg x plus L divided by 2L. And we already know that the summation of the both the normals is equal to mg. Therefore we know that our normal right plus normal left is equal to our mg. So from here if we substitute, or from here we can write our normal to the left will be equal to mg minus normal to the right, and we substitute our normal to the right, we are going to get this our mg minus of mg x plus L, and this is 2L. So from here we get that the normal to the left will be equal to, if we take our 2L mg we can take as our common, and 2 our LCM, 2L our LCM will be, so this will be 2L minus x minus L and divided by 2L, which will be coming as mg upon 2L, and we can write this as L minus x. So we got the normals equation towards the left as well as towards the right. So it means when x is equal to 0, we can say that our normal toward the left will be equal to normal to the right, and they both will be equal to mg by 2. Okay. And our, if x is greater than 0, okay, so therefore we can say that our normal to the right will be greater than our normal to the left. This is the basic equation. Normal to the right is our x plus, and towards our left is L minus. Now we come to our frictional forces. And so in the question it is mentioned that the rollers are rotating rapidly, so therefore the bar's velocity is negligible compared to the roller's tangential speed. And we already denoted the value of the friction, and let me also modify it. Let me call this as FL and F. This is F left and this is F right. So we have two value of frictions, FL and F right. So for left roller, the frictional force is our FL, which will be equal to plus mu and the normal, okay, and its direction will be towards right. And we have our right roller, so this will be friction to the right. Friction of the right roller will be equal to minus mu, and this is our R, and its direction will be towards the left. Okay. Therefore we can say our net horizontal force, net horizontal force on the bar. And this net horizontal force, let us suppose, is of F will be equal to FL plus FR, and this gives us N and mu of NR. Okay. And because we knew N, L and NR, so we can find out our F. So F mu we can take as common. So we have a left side, we have our mg upon 2L, we can take common from both, and we get this as L minus X plus, sorry, not plus but minus L plus X. So here our if you open it, this will be coming as minus and this will be also coming as minus. So L and L going to cancel out. So this will be minus of X and minus of X, which will be coming as, this will be our minus of 2X. So we get this as mu mg 2L and minus of 2X. So here this 2 and 2 also cancel out. So we get that our force F will be equal to minus and we have this as mu mg upon L times x. Now we can write, because we found out our net force, now we can write the equation of the motion. Equation of motion, and that equation of the motion, because there is only translational motion in x direction, therefore we can write that the mass second derivative, that is its acceleration with respect to x, will be equal to the applied force F, and applied force F is our minus mu mg upon L times x. Now it is almost done, so we get the equation as x double derivative, which is our acceleration, will be equal to, here this mass and mass cancels out, so we can just write it as, this will be x and acceleration, that is x double derivative, plus it will be coming as mu gl times x is equal to 0, and this equation is equivalent to our SHM equation, which is our x double derivative plus omega square times x is equal to 0. Therefore from here we can say that our omega square is equal to mu g upon L, or which gives us that the angular frequency is equal to mu g upon L and its square root. So this is our equation of motion. So we proved that it is executing SHM, because this is our equation of SHM, and we found out its angular omega. So this completes the first question. We come to the next question, and it states that a solid cylinder of mass m and radius r is rotated in a uniform V group with a constant angular speed omega. The coefficient of friction between the cylinder and each surface is mu. Find the torque that must be applied to the cylinder to maintain its constant rotation. So here you can just draw the basic diagram, and we are given that we are having a V groove. So this is, first of all let me draw a solid cylinder, then we can draw with respect to, so this is a solid cylinder and it is placed inside a V groove. So this is a V groove. So this will be the complete figure. And it is rotating with some angular speed. Okay, so let us assume that it is rotating in this direction with the angular speed of omega, and its radius is given as capital R. So this is our radius, and its mass is given as capital M. And the other forces, there will be two contact forces, and these contact forces is, suppose this is our N1, and other side we are going to have our N2, and it is rotating, so there will be the frictional force also that is going to provide the necessary torque so that it will rotate. So in this case we have to remember that no doubt we have a same block, so this block is same for our this left point as well as to the right point also, but as it is rotating, so this normal has to be different, they cannot be same. Okay. Secondly, the value of the friction will also be different. Okay, so we have to keep this in mind, and we can draw the direction of friction. So on the right side, let us call this friction is F2, and on the left side, let us call this friction as F1. So these are the various forces that are acting on it. And one more, there will be mg, vertically downward. Okay. So it is given, or we can draw a conclusion from the question itself also, that it is only rotating. Okay, so it means there is no translational motion. So the net horizontal forces will be equal to 0. Okay. There is only rotational motion. So we can say that the center of mass of cylinder remains stationary which basically means that no translational or we can say net horizontal and vertical forces is equal to 0. Net horizontal and vertical forces is equal to 0. And rotation is because it is saying that it is having a constant angular velocity. Okay. So therefore we can say that rotation is steady. Okay. And because the direction of the rotation, like we said, it is rotating from the our right side toward the left side, so therefore the frictional forces will cause an asymmetric motion, and that is going to lead towards unequal normal. Okay. So you can say that due to direction of rotation, the frictional forces causes an asymmetry leading to unequal normal forces on the two surfaces. On the two surfaces. And so this is the basic premise of the question, and from here we can also say that the value of our F1 in terms of normal, we can write that our F1 will be equal to mu n1, and we can say our F2 is equal to mu n2. And we can also find out their directions. that our so let us call this as point A and this is point B. So we have point A and this is normal our N1. We have a frictional force F1. So obviously this angle will be 90 degree, and if we draw a horizontal line, so we are going to get the angle with respect to the horizontal of the normal will be equal to 45 degree, and this is true for our F2 also. So we can draw this for F2 also same. Okay, so this is our point B and we have a normal here N2. This is our V groove surface, and on this we are having our F2, and with respect to our horizontal this angle will be our 45 degree. And okay, so let's find out the equilibrium forces, because like I said that the forces will be equilibrium in horizontal as well as in vertical. So let us analyze the force equilibrium. And for that we are going to resolve the forces in x direction as well as in y direction. Okay. So let us first of all the vertical forces, or we can say in vertical direction. And the net is equal to 0. So we can here we can just, so we are going to have our N1 and so in the okay let me, so this angle will be also 45 and this angle will be also 45. Okay, so it doesn't matter much. So therefore we can write that our vertical components, normal vertical components, we can say that our N1 cos of 45 plus N2 cos of 45 is equal to 0. And we have a frictional vertical frictional components. One second. Sorry. Sine. Sine of this. Okay. And now we come to our frictional part. Vertical components. And frictional vertical components. one will be let me draw it here. This is our F1. So this will be horizontal component and vertical component, and this is our A, and this is our B, and this is our F2. So therefore this will be two component. So we can clearly see that its vertical component will be entirely in opposite direction. So we can say this will be our F1 sine of 45, and this will be F2 sine of 45. Okay, other one will be our cos. Therefore our vertical components will be coming as F1 sine of 45 minus F2 sine of 45. This we can add later on. Now we can find out there will be also our mg that will be acting in the downward direction. So we have a vertical force mg, vertical weight, which is our mg. Therefore we can write that because the normals are also acting upward, and net force we found out is our, so we have our, this is our N1, N2, and our F1 and F2, and we are having our mg. Okay, so these are all the vertical forces acting. So we can just add them, and with respect to the direction, and that summation will be equal to 0. Therefore, and this is N1 x component, F1 x component, N2, sorry, not x but y component, y, and y component. Therefore we can write that our N1y plus F1y minus mg minus F2y plus N2y is equal to 0. So this is all the forces which are in vertical direction. So we simply substitute their values which we have already calculated. Okay. Therefore we can write that our N1 sine of 45 plus N2 sine of 45 plus F1 is our F1 sine of 45 minus F2 sine of 45, and that will be equal to our mg, and all these sine values will be same, 1 by root 2, 1 by root 2, 1 by root 2, 1 by root 2. Okay. Therefore we can write that our N1 plus N2 plus F1, and in terms of this F1 and F2 we can write it in terms of our normals, that our mu N1 minus mu N2 is equal to mg times square root of 2, and we can take this mu as common, so this will be coming as this equation. Okay. Let us call this equation number 1. Same analysis we are going to do for our horizontal direction. You can say for horizontal direction, and that will be also equal to 0, and there is no mg component in the horizontal direction, and the forces, that is our, this will be our F1 cos 45, F2 cos 45, and the normals will be our F1 cos of 45, and there will be F2 cos of 45. Okay, so these will be all the forces. So let me draw it here. So this is point A, sorry, yeah, so this is point A, and this was point B, and similarly we can say that our point A, we are going to have a F1 x, and its frictional is towards the right side, so this is our N1x, and the frictional part will be our F1x, and towards our point B we are going to have our F2x, and normal is frictionally downward direction, it's normal. So this is our N2, and both friction, these are N1, this also N1. So we have normal and frictional component in the same direction. So this will be our F2x. So we can write that the equation will be equal to our N1x minus F1x minus N2x minus F2x is equal to 0. Okay. And if we substitute there, because it is sine and cos, so square root of 2 will be same, so we can just write it directly. This will be a square root of 2, and we are going to have this as N1 minus, in place of F1 we can write our mu N1 minus N2 minus mu N2, and is equal to 0. So we can just ignore this part because it cannot be equal to 0. So from here we can write that our N1 1 minus mu 1 minus N2 1 plus mu is equal to 0, and we can say that our N2 is equal to our N1 1 minus mu divided by 1 plus mu. And let us assume, because we have to find out N1 and N2, so let us assume this ratio is equal to K. Much more easier to solve because it will be, so we assume this part, therefore we can say that our N2 is equal to K times N1. So now from equation 1, so you can say from equation 1, we substitute this n2 as k times n1. We get this as our n1 plus k times n1 plus mu n1 minus k times n1 is equal to mg square root of 2. Now we can just take n1 throughout common, because this gives us n1, and we are left with 1 plus k, and we have this as mu, and we have 1 minus k is equal to mg square root of 2. And now we are supposed to find out this 1 plus k and 1 minus k, then we can substitute it here. This is only solution part now. Most of the things are done. So we get this as 1 plus k will be equal to 1 plus 1 minus mu and 1 plus mu. So that will be coming as mu and mu are going to cancel out. So we get this as 2 upon 1 plus mu. Similarly, we find out 1 minus mu, 1 minus k will be equal to 1 minus mu and 1 plus mu. And this will be minus 1 plus mu. So 1 and 1 is going to cancel out. So this will be coming as 2 mu upon 1 plus mu. And then we require it multiplied by mu. So this we get mu 1 minus k will be equal to 2 mu square and 1 plus mu. And then we are going to write this complete equation, and we get this as 1 plus k plus mu 1 minus k, and this comes as 2 upon 1 plus mu and plus 2 mu square upon 1 plus mu. So 1 plus mu will be our LCM. 2 we can take as common, so this comes plus 1 plus mu square. Now we simply substitute it here. We get this n1 times 2 1 plus mu square 1 plus mu is equal to mg root 2. So we get our first normal, that is our n1. So n1 will be equal to our mg 1 plus mu multiply and square root of 2 divided by 2 1 plus mu square. Okay, we can just rationalize it if required, otherwise we can keep it according to the question. And similarly, we can get our n2 will be equal to mg 1 minus mu square root of 2, and this will be 2 1 plus mu square. So we got our normals. Now we come to our torque calculations. And the frictional forces, they are going to, you can say each frictional force is our F is equal to mu n, and that is going to act as a tangential at the point of contact, which is we have already drawn in the figure, and they are at a distance of r from the point of rotation, which is their center. Okay. So once again we can just, so we are having this as a center, and we have our F1, and here we are having F2, and each of this force is at a distance of r from its center of mass. That is our center of mass or axis of rotation. Therefore, we can say that our and this is our omega. So both the frictional forces are the same direction. Okay, so we can say that total frictional force, or we can say torque due to frictional force. So we can say that our total frictional torque torque, let us call this as tau f, and that will be equal to torque because of the first frictional force and torque because of the second frictional force. And we can write that as total our frictional force tau 1 will be equal to our F1 times our R and F2 times R. So we get this as F1 multiplied by R plus F2 multiplied by R, and F1 and F2 we already know in terms of normal, so we can write this as a mu N1R plus mu into R. So we can take this common, so we get our frictional force tau will be equal to mu N1 plus N2 times R. And we are supposed to calculate N1 plus N2. We already know what is our N1 and what is our N2. So we simply substitute them and get N1 plus N2. So we have a N1 plus N2, and in N1 plus N2 the denominator as well as few terms of numerator will be common, so we can just take them as, so we get this as mg square root of 2, and denominator will be 1 plus mu square, and inside we are going to get this as 1 plus mu plus 1 minus mu. So this mu and mu going to cancel out, and this will be 1 plus 1, that it will be 2, and this 2 and 2 going to cancel out. Therefore we get that our N1 plus N2 N1 plus N2 will be equal to mg square root of 2, and this comes as 1 plus mu square. Okay. Therefore we can say that our torque tau f, this will be coming as mg mu square root of 2 and multiply by r, and this will be 1 plus mu square. Okay, and this is our value of our torque. Okay, so in this case, if you look closely, we see that this particular expression of the torque does not have omega. It means the frictional force is independent of speed, and you can say the torque is going to balance the opposing frictional torque. Okay, so there is no omega present in this final expression of the torque. Okay, so the frictional force is independent of speed, and everything is constant in this. You can say our radius is constant, mg is also constant, mu is also constant. So this torque is more or less, we can say, is constant. So next question. It states that a wheel is attached to a fixed shaft. The system is free to rotate without friction. To measure the moment of inertia of a wheel shaft system, a tape of negligible mass is wrapped around the shaft and pulled with a known constant force F. When the length L of the tape has unwound, the system is rotating with a constant angular speed omega naught. Find the moment of inertia I naught of the system. So this is a shaft wheel system. So we can just draw an approximate figure. Suppose this is our shaft, and around it we are having a wheel, and around this shaft we have this tape wound. Okay, so there is a tape wound on this shaft, and we are pulling this tape with the force F, and it is given that when this length of the tape is L, so let us suppose this is the length of the tape, the system is rotating. It means the wheel will be rotating at a angular speed of omega naught, and we have to find out what will be the moment of inertia when our angular speed is omega naught. So let's assume that you can say that this is basically directly we can approach this question using two methods. First, we can use our work energy theorem, and based on this we can just also find out, and other part we can use our basic rotational dynamics considering the torque, etc., and that is also going to solve the questions. So first of all we are going to try to solve it using our work energy theorem. So we have method 1, and this method 1 is our work energy theorem. And this work energy theorem, because we have a force F which is going to do the work so that the tape unwinds, and the displacement is said to be our L. Okay. And it is said that F is a constant force. So we are given that force F does work on the system and it is also given that the displacement of point of application of F, that is our force F is L, that's the unwind length of the tape, and F is constant as well as tangential. F is our constant and it is also tangential. Therefore, we can say that the work done by the force F will be equal to our FL. Okay. And there is said that there is no friction, so obviously there will be no losses. So we can say that this entire work done, that is our W, will be converted into the kinetic energy system. And initially the system was at rest, so therefore the initial kinetic energy was equal to 0. We can say that no losses therefore all work converts into rotational kinetic energy of the system. And initially the system was at rest. Initially system is at rest, therefore kinetic energy initial will be equal to 0, and the final kinetic energy, because there is only rotational motion, so final kinetic energy is, suppose our KEF will be equal to our half I naught and omega naught square. So these two will be equal. Work done will be equal to the total kinetic energy. Initially 0, so that will be equal to our KEF. Therefore we can say that work done because of the force F will be equal to our kinetic energy initial plus kinetic energy final. And from here we can write our FL is equal to half I naught omega naught square. And from here you can easily find out of I naught. So we get of I naught will be equal to twice FL, and we have this as omega naught square. And same we can find out using the rotational dynamics, which means considering the torque and everything. So we have a method 2. And we can say this as a rotational dynamics. And first of all, let's find out the torque. Torque due to force F, and that is our tau is equal to F multiplied by radius is given to us. Radius is not given to us, so let us assume that is small r. And our this torque is going to produce the angular acceleration. So we can say that our angular acceleration is our alpha is equal to torque about its moment of inertia, and which gives us F times R, and this is I naught. And in this case, this R is our radius of the this is our small r. And we can find out that the length of the tape unwound is L. So corresponding, let us assume that the angular displacement of that shaft is theta. So you can say for length L, the angular displacement is theta. Therefore, we can write that our theta will be equal to L upon R. Okay. And initially it was at rest, so we can use our equation of kinematics, and we can write that equation of kinematics for rotation, and this rotation is from rest. From rest we get final angular speed is given as omega naught, so this omega naught square will be equal to 2 times alpha times theta. Initially it was 0. Therefore we can simply substitute all the relative things here, so we get this as omega naught square is equal to 2 times torque is the angular, this is Fr upon I naught, and theta is our L upon R. So here this R and R cancels out, therefore we get from here that our I naught will be equal to 2FL, and this we have omega naught square. So which is same. So we can solve this question in either ways. In both the cases we are going to get the result. And we can also use it, sometimes we can also if we want to solve it in terms of linear, we can also get the same answer. Okay. And okay, let's solve it using the linear speed v. Because for that also we can get the same answer. Let's try that also. Okay. And we have a third method. Okay. And let us suppose that the linear speed of the unwinding point is v. So for that, let us suppose that linear speed of unwinding point is our v, and this v will be obviously equal to r times omega, and omega we can write this as our r times alpha t, and the total unwind length is of L. Total unwind length is of L, and that L we can find out by integration of this velocity with respect to time t, and let us call this as t dash so that it is easy to substitute. We can call this as any variable in terms of t, and this is from 0 to t, and we substitute our v, so this comes as 0 to t, and this is we have r alpha t times dt prime. Therefore it is simplest of our integration, so this we get our L is equal to 1 by 2 and we have this is r alpha t square, and t is our nothing but our omega naught upon alpha, and we substitute it, we get this is L is equal to our 1 by 2 r alpha, and this will be our omega square upon alpha square. This alpha and this square cancels out, and from here we get that our alpha is equal to this will be coming as r omega naught square, or we can say omega naught square r divided by 2L. Okay, and we have also calculated our alpha from our previous expression. Let me write it there. So we also know that our alpha is equal to Fr upon I naught. Okay, so we can just equate them. So we get that omega square naught r 2L is equal to Fr upon I naught. Here r and r cancels out. Same expression we are going to get. I naught is equal to 2Fl and divided by omega naught square. Same. Okay. But here we have to remember that we have taken the linear speed of the unwinding point. Okay. So we have taken the linear speed of this point. Okay, moving in this direction with v. Next question. It states that a man of mass m stands on a railroad car that is rounding an unbanked curve of radius r at a speed v. His center of mass is at a height L of the car. Its feet are separated by a distance d. The man is facing the direction of motion. Find the weight supported by each of his feet. So this is the basic question, and we are going to modify this question into certain ways. Like in the first part, it is facing direction of motion. Then we can say that what is going to happen if it is facing opposite side to the direction of motion. And here it is mentioned that their feet are separated. So what is going to happen if this distance becomes approximately equal to 0? And when the distance becomes approximately equal to 0, or we can say the feet are very close to each other, we are also going to find out what will be the various subparts of that. Okay, so let's first of all solve this part. So we are given that it is, we are having a railroad and it is okay. So let me try to draw the figure. So we have a railway track, something like this, and on this we are having a car, railroad car. And the radius of the curve is given to as r. So suppose this is center and this radius of the curve is our r, and the person which is standing on it, it is difficult to draw the person. Okay, let me try it. So the person is standing on it such that its feet are at a distance. So suppose this is its left feet and this is its right feet, and it is standing somewhere like this. Okay, Okay, so this is the person. Doesn't look like, but let's assume. And d is the distance between its feet. And the center of mass is a height L. So suppose this is center of mass and this is a height of L. So obviously here it will be mg in the downward direction. And there will be two normals, and one normal on the left feet, other normal on the right feet, and there will be also the frictional forces. This will be F1 and this will be F2. Later on we can just draw this figure in the broader sense also. Okay. And let us call this as point as A, this point as A and this point as B. So we have point A, point B, and in this case we have our normal on the left is NL, normal on the right is our NR, and the frictional force is our FL, and we have our FR and mg in the downward direction. Okay. So in this case, and the distance between its feet is given as d. So we assume that this center of mass is our origin. So to the left side we are going to have minus d by 2, and on the right side we are going to have plus d by 2, and this is our x-axis. Okay. And this x-axis is on this. So forces on the man. So like I said, there will be weight, which is a mg acting downward along the center of mass, and we have a normal on our left foot, which is our NL, and this NL, and then we are going to have a normal on the right foot, which is our NR. We are going to have a frictional force, frictional forces, and the frictional forces on the left will be our FL, which is our mu times NL, okay, and its direction will be towards the left, okay, toward the center of the curvature. And then we will have a FR, which will be mu times NR. Its direction will be also same, and this frictional force is going to provide us necessary centripetal forces. So now we can write the equilibrium equation, because there is no for in vertical as well as in horizontal direction. Okay. So we can say equilibrium equations. First, let us write it with respect to our vertical direction. And in the vertical we have our normal in upward and mg in downward, so we get our NL plus NR is equal to our mg. And horizontal, direction, we are going to add this as FL plus FR, and that is centripetal force, that is our mv square upon R. And we substitute our FL and FR in terms of normal, so we get this as our mu can be taken as common, so this is our normal to the left plus normal to the right is equal to mv square upon R. And once again, yes, so and this NL plus NR is equal to nothing but our mg. So if you want, we can just find out that also. So this is mu times mg, this comes as mv square upon R, and this m and m cancels out, so we get our mu is equal to v square upon gr. So from this expression we can clearly see that the mass of the object, which is here it is m of man, is not in the frictional force, coefficient of friction. Okay, now let us find out, because also there is no rotational motion, everything is in balance, so let us find out the torque balance also. As there is no rotation, about center of mass, and there are total 4 forces: N normal left right, frictional left right, and there is mg. So this is, we can just draw it in the form of a table. So this is a force, and then it will be our torque is lever arm, and that is our value of the torque. So the first force is our normal to the left, direction is upward, and we have its distance d by 2 to right of our center of mass. Okay. One second. To the left of our center of mass. This is our left, and this will be clockwise and counterclockwise. We can take negative and positive. Okay. So let us consider this will be our clockwise, let us consider positive, and counterclockwise let us consider negative. Okay. And this will be giving us minus of NL times d by 2, and next we have our, to the right direction is also upward, distance is our d by 2 and it is toward the right, and this will plus nr d by 2. Then we are having our mg, which is downward direction, and this is acting at the center of mass, so it will be 0. And then we have our frictional force FL and FR. So FL and FR, and both are acting towards the left side, and it is both are at a distance of L from the center of mass, so the torque direction will be same for both, and this will be our plus FL FR multiplied by L, and FL plus FR is our mv square upon r. So this comes as our mv square upon r times L. So now we can just write the equation summing that torque should be equal to 0. So we can say that our mv square upon r times L plus d by 2 we can take common from our normal torques, and that will be equal to our nr minus nl is equal to 0. And from here we can say that our right minus left will be equal to minus of twice mv square L and divided by dr. So let us solve them. We have two equations, and first equation is our, let us put this one, and this is our second equation. We simply add them. Equation 1 plus equation 2, and here left, let me write it here, nr plus nl plus nr minus nl is equal to mg minus 2 mv square L upon dr. And here this left and left cancel out, so this comes as twice of our nr. So you can say our nr is equal to mg by 2 minus mv square L upon 2 cancels out, and this comes as our dr. Okay. So this is our normal to our right foot. Okay. And similarly, if we subtract these two equations, we are going to get normal to our left foot, which will be same except one sign, that will be a plus and mv square L upon d times r. So from here at least we can say that the weight supported by our right foot will be less and by the left foot will be more. So we can say our right foot weight supported by right foot will be less than weight supported by left foot. Okay. Now if we say that the man is facing opposite to the direction of the motion. Okay. In this case, we have to also remember that this right foot is closer to the center and left foot is away further from the center. Okay. So based on this, we can just draw a conclusion that even though even if it is going to face in the opposite direction, the basic, this left and right, is going to will be same. But there we have to remember that it will be closer to the, you can say, center and farther from the center. Okay. So that is, in this way, it is much more easy to remember. Okay. So let me write it down that normal on the feet closer to the center, closer to the center. Okay. And further to the center. So even if it is facing in the opposite direction, the basic formula is going to remain same. It means closer to the center and further to the center. So closer to the center will be our weight will be on the lower side, because that will be right foot, and the left foot will be further from the center. So the expression is just going to change. Okay. So let me write it in this way. We can say that closer to the center this will be giving us mg by 2 plus mv square L upon d times r, and we have further from the center and that will be equal to mg by 2 minus mv square L upon dr. So that will be the only change. The rest of the calculation will be same. Okay. And this is when it is facing away from the opposite direction of the rotation. Opposite to the direction of the motion, not rotation, but opposite to the direction of the motion. Okay. Now, if we look closely in this expression, that when, like I said, if this d becomes very small, or we can say approximately equal to 0, so it means the feet distance is very small. So let us discuss that part also. Okay. So we can say the feet are together such that we take them as a single point contact. Single point contact, which means that d is approximately equal to 0. So if we look closely in these two expressions, if you put d is equal to 0, the entire calculation will be our, you can say, it will be basically it will be giving us a result as infinite. Okay, so it means the stability or equilibrium position will be disturbed. So because of that, the man is going to, or we can say the body is going to tilt. Okay, and we are going to find out by how much amount that body is going to tilt. Okay. So we can say when the feet are together, so based on this we can say by how much the body should tilt with respect to vertical. So basically means that previously the person was standing like this, okay, so distance is very close to 0, and now it is going to tilt somewhere in this direction. Okay, so we have to find out with respect to vertical. Suppose that angle is theta, because here the distance we have assumed is close to 0. And let us suppose that angle is our theta. And for this case we are going to analyze using the non-inertial frame of our railroad car, or we can say car. So where our fictitious centripetal force will be also come into the picture. So we can say that analyzing in non-inertial frame, and therefore you can say the fictitious centrifugal force that is our F C of F will be also our mv square upon r. Okay, and it will be acting horizontally outward on the center of mass. So once again we assume that the curve is toward the center, which was our previous discussion, and the centripetal force, or centripetal acceleration will be left inward. Same conditions we are assuming that our curve is left, and therefore our centripetal acceleration will be left inward. So it means we are going to have a curve which is like this, and the centripetal action will be left inward. And like we said that the man tilts left side by theta. So we can say our man tilts leftward by theta. So we can say that the horizontal displacement of the center of mass horizontal displacement of center of mass, let us suppose that will be inward. Let us suppose that is our delta, and this delta will be equal to our L sine of theta. Okay, we can just draw an approximate figure for that also. So initially this was our center of mass, that is our A, and its length is given as, height is given as L. Okay. And now it is moved at an angle of theta with the vertical. Okay. Let me draw it otherwise. So moved with respect to theta with the vertical. So we get this will be equal to L sine of theta, and our vertical height of center of mass vertical height of this center of mass, let us suppose that is our H, it will be equal to our L cos of theta. And next is our force equilibrium. So we can say force equilibrium and we assume that it is a single point contact, therefore the single point contact will be our, normal is our N, and mg will be in the downward direction. Okay. So we can say that our N is equal to mg, and single point contact, so therefore we have only one frictional force, that is F, and that will be balanced by our the centripetal force. So we have our vertical, this was our vertical, and our F will be equal to mv square upon r, and this will be our horizontal. And now we can find out the torque equilibrium about the point of contact. Torque equilibrium about point of contact. And so obviously this net sum of the torque, and torque will be produced by our normal as well as the frictional force, because this mg will be along the center of mass. Okay, so their torque should be equal to our okay. So we can say that if there is no tipping, then the torque sum should be equal to 0. So we can say for no tipping, we should have torque sum should be equal to 0. And so let's find out our torque due to weight mg. and which will be mg is acting in downward direction. Therefore, you can say that the position of the, or that we can write directly formula also. See, torque because of mg will be equal to mg, and the displacement is the small one, which is our delta. And now we come to our torque due to our, what force we call that, the fictitious centripetal force. So we can say torque due to the fictitious center of centripetal force, and that is our that torque, let us suppose tau Cf will be equal to the force multiplied by the distance, that is our height h, and that will be in opposite direction, we can say negative. And we substitute this formula, which is our mv square upon r times h, and their summation will be equal to 0. Therefore, we get that our net torque should be equal to 0. So we can see our mg times delta minus mv square upon r times h is equal to 0. Here this mass cannot be equal to 0. Therefore, we can write that our delta is equal to v square upon gr times h, and we know that our delta is our L sine of theta and our h is L cos of theta. So we substitute them. Delta is our L sine of theta, and we have this as v square, gr, and h is our L cos of theta. And here this length and length cancels out. We get this as our tangent of theta is equal to v square upon gr, or we can say our theta is equal to tangent inverse of v square upon gr. And if you require, because this v is the linear speed of the center of mass, if you require, we can substitute it with respect to the angular velocity also. Okay. So this is the angle of our tilt. And in this case, this is a basic expression. I think you must have seen it with respect to the usually we deal it with respect to the cycle motion in the rotational motion. There is a concept of cycle, tilt of the cycle. I think that expression is also the same. And now let's find out what will be the maximum car speed, okay, so that it prevents slipping, without slipping. So you can say the maximum speed without slipping. So we know that only the force, that is the frictional force, will be there, so that the maximum, there is no slipping of the car. And because it is a single point contact, therefore we can say that a frictional force which is F is mv square upon r. Obviously it will be towards our left side, and our maximum value of friction, so this is our frictional force F, that is our Fr, and maximum available friction is suppose our F max, and that will be equal to our mu times n, or we can say mu times mg. And for without slipping, same condition will be there, that our F of r should be our less than equal to our F of max. So we substitute them, we get our mv square upon r is equal to less than equal to mu times mg, and this mass and mass cancels out, so we get that our maximum value of our velocity without slipping will be equal to, first of all let me sort it out, we can write this as v square less than equal to, or v is less than equal to this will be mu g r square root. So therefore maximum value of velocity will be equal to mu g r, and this is without slipping. Okay. And we can also find out the radius of that curve, so that there is no slipping. So we can say the minimum value of radius r, let us call this as r mean, means minimum value of the radius of the that curve without slipping. And same condition we can use, that is our mv square upon r should be less than equal to mu mg, and from here we can say that our r should be greater than equal to mu square upon mu g, and therefore we can say that the minimum value of our radius will be equal to v square upon mu g. And if required, we can also find out the maximum value of the static friction. Okay. And that is minimum required coefficient of friction, that is mu mean. Same concept we can use, that mu is greater than equal to v square upon gr. From here we can say that the minimum value of the coefficient of the static friction will be equal to V square upon GR, and all these calculations are based that there is no slipping. So these were the few variations of the railroad car. Next question is it states that a 3000 kg car is parked on a 30-degree slope facing uphill. The center of mass of the car is located halfway between the front and the rear wheels and is 2 cm above the ground. The distance between the front and rear wheels is 8 cm. Find the normal force exerted by the road on the front wheels and on the rear wheels. Okay. So we are also going to modify this question according to some parts. In this case, we are given that it is facing uphill. In the second, we can assume that it is facing downhill and how the situation is going to change. Okay. So first of all, let us solve it when it is facing up the hill. For that, we can just draw the figure, and theta is given as, let us suppose it theta, then we can generalize it, and we have our rear wheel. So this is suppose our rear wheel and this is our front wheel. Okay. And we can just draw the car like this. It is facing upward, little like this. So we have to remember that it is facing upward in this direction. And we are given that the distance between the front and rear wheel is 8 cm. So in this case, let us assume that our rear wheel is our origin. Okay, so this is our origin having coordinate 0, 0. And the distance between the wheels is, let us suppose, our L. And let me suppose the horizontal distance between the rear and front wheel is our A, and the vertical distance of the front wheel from this axis is, let us suppose, B. And obviously this angle will be our theta, which is given to us as 60 degree. And this is our x-axis and this is our y-axis. And we assumed that the real wheel contact point is origin. Real wheel contact point is our origin, 0, 0. So therefore we can say that the front wheel's contact point horizontal distance front wheel contact point horizontal distance, which we have called as A, and that A will be equal to our L cos of theta, and this length is given as 8 cm. Therefore we can say that our A will be equal to, this will be 0.8 0.08 cos of 30, and that will be square root of 3 by 2, so we can say that will be equal to 0.04 times square root of 3, and we can say that our vertical height of the front wheel which B will be equal to L sine of theta. So we get our B is equal to, this is 0.08 sine of 30, that is 1 by 2. This gives us 0.04, and okay, let me draw it here. This is our rear wheel and this is our front wheel, and we found out our A and we are B, and this distance is given to us. Okay, and let us assume that the midpoint is somewhere here, and this will be L by 2, so this will be coming as 0.04. This will be 0.04. And we can find out the x and y coordinate of this midpoint. Okay, so this is our center of mass. So we can say that our center of mass, we are going to have our x coordinate, let us call this as x midpoint, because this is the midpoint of the vehicle. So x mid will be equal to our same formula, and this is only distance will be 0.4, so this will be coming as 0.02 square root of 3, and this gets y midpoint, that will be equal to 0.02. This is our center of mass, and therefore we can say that this x mid, we can also call this as h height, okay, because that we can use is one second. Oh yes, not h. So let us say you can say that our center of mass is displaced h is equal to 0.2 perpendicular to the slope from this midpoint, from this midpoint. Therefore, we can write the coordinate of our center of mass. One second, let me check. 0.4 x mid. Okay, so we can say that center of mass coordinate let us call this as our xcm will be equal to our x mid, and this will be plus the displacement of its height h, that will be plus h, and this will be our minus sine of theta. So we get that our xcm, let me write this as ycm also, then we can calculate it, and our ycm will be equal to y of midpoint plus this comes as h cos of theta. So we get this as xcm will be equal to 0.02 square root of 3, and this is plus h is our 0.02, and this is minus of theta, that is our minus 0.5, which is giving us 0.02. we can take as common, so this comes as square root of 3 minus 0.5, and we get our ycm. Ycm will be equal to y mid, which is 0.02 plus 0.02 and cos of theta, that will be our square root of 3 upon 2. This comes as our 0.02, and we have 1 plus square root of 3 upon 2. So these are the center of mass coordinate, xcm and ycm. So this is xcm and ycm. Now we are going to do for our force balance and torque balance, because the entire system is in equilibrium. So let us solve the force balance. And we have two normal forces, and front let us call this as NF, and the rear let us call this as NR, and that will be acting perpendicular to the slope. So we have a slope, and here let us call this a normal force as N rear and N front, and they will be acting in the direction of our angle is given as theta, and we have taken them, this is our origin, this is x-axis, and we have y-axis, and this is our origin. And we are having this mg in the downward direction, so we can divide this mg into two components, angle theta, so we have mg cos of theta, and we have mg sine of theta, and there will be, along with it, there will be two frictional forces, and the both frictional forces will be in upward direction. So this is F of rear, and we have our F of front. Okay. So let us, first of all, we have our perpendicular to the slope force balance. perpendicular to the slope, and perpendicular to the slope we have our normal nr plus nf, and that will be equal to our mg cos of theta. And then we having parallel to the slope, and parallel to the slope is our right plus front, rear and front is equal to mg sine of theta. Sine of theta. Okay. And we can find out their both values. So we get our nr plus nf. Mass is given to us as 3000. So this comes as 3000 times g, and cos of theta will be equal to square root of 3 divided by 2, which comes as 1500 g and square root of 3. And we get this as frictional to the rear, frictional to the front will be equal to 3000 g, and this is our 1 by 2, which gives us 1500 g. So these are the sum, both the forces. And now we come to the torque balance. And so let us find out the torque about the rear point of contact. Okay. So we are going to calculate torque at rear point of contact, that is at the origin whose coordinate is 0 and 0. So therefore the normal, because of, oh, 1 second, I forgot, here it will be, because this is origin, this will be our nr. nr, and this is our frictional. Okay, because rear is our origin. Sorry. And so because of this, we can say that the torque from the rear, that is normal, and because of the frictional force will be equal to 0. So we can say that torque from our normal rear and frictional rear will be equal to 0, because they are acting at the same point, that is our origin. And torque from the weight let us call this as tau mg, and this tau mg will be equal to our mg, and it is x, coordinate of center of mass, and we assume it is negative. And then we have our torque due to our front normal, torque from nf, let us call this as tau f, and that will be equal to our normal multiplied by our length, that is our lever arm. Okay, and next is our torque from our frictional force, which is on the front wheel, and that will be equal to our 0. And now we can just set that the torque should be equal to, because it is in equilibrium, so net torque should be equal to 0. Therefore we can say that our net torque should be equal to 0, or we can say our minus mg xcm plus nf times L should be equal to 0. So from here we get our nf will be equal to mg xcm and divided by L, and we simply substitute their values. We have our mass is our 3000, so this comes at 3000 G. Length is our 0.8, and xcm we calculated, this is our 0.02 square root of 3 minus 0.5. So we get that the NF, one second, this is capital F. Normal at the front will be equal to 375 G, and this comes as 2 square root of 3 minus 1. And let us calculate the torque about the front contact point. Torque about front contact point, and the front contact point is our 0.04 square root of 3 and 0.04. So obviously because of the front, normal and frictional both will be equal to 0. So you can say our torque due to normal in the front and frictional force because of front will be equal to 0. And torque from the rear, torque from our normal at the rear will be equal to minus nr times L, and torque from our frictional force at the rear will be equal to 0. And now we come to the torque from the weight. Torque from weight will be equal to minus mg, and that is our x cm, and it's minus of a, that is a horizontal distance with respect to a. Okay, because we are going to find out it at the front part, because the distance will be our xcm minus a, because a is the total horizontal distance between the front and rear, and xcm is the distance from the midpoint to the origin. So once again, our net torque is 0, is equal to 0. therefore we can write that minus normal at the rear multiplied by length L, and we have this is minus mg, and our axiom minus of A is equal to 0. Therefore we can write normal at the rear will be equal to, we get this as mg, and in order to make it positive we can write A minus axiom upon L, and we simply substitute the values, and we have our mass is our 3000 times g, length is 0.08, and our A is our 0.04 square root of 3, 0.04 square root of 3 minus, and our axiom was our 0.02, and this is our square root of 3 minus 0.05, square root of 3 minus 0.5, and this calculation will be giving us that the rear will be equal to 375 g times 2 root 3 plus 1, and front was our, we didn't calculate front, yeah, we calculated front, so only difference is of this sign, minus as well as positive. So these are the normals that are associated with the front as well as rear with when it is facing upward. And if we assume that it is facing downward, down the hill, face is facing down the hill, we can say that car face is downhill. Okay. So in this case, our front normal will be equal to 375 g times 2 square root of 3 plus 1, and rear is going to have same but different sign, minus 1. Okay. So this will be only the change that the front and rear are going to interchange. Okay. And in this case also we can find out the tipping angle, the angle at which it is going to lift. Okay. And the calculation will be same as in the both the cases. So first of all, let us solve it for tipping angle. And for tipping angle, let us assume first case is our downhill facing. So downhill facing, as it is about to tip, the normal at the rear will be the first to come off. Okay. So you can say when downhill, the normal at the rear, that is our NR, should be equal to 0. Okay. So which basically means that our rear wheels lift off. The rear wheel will be first which will be going to lift off. So therefore we can say that the torque about the front wheels, torque about front wheels and